Low noise amplifiers, or LNAs, are critical components of any system. An LNA can be designed with a discrete transistor, which would involve designing an input matching network to achieve low noise figure. Another approach when designing an LNA is to use a mimic LNA that's already internally matched to 50 ohms. This would seem like the easier approach because there's no need to design any matching networks. Just insert the device into a 50 ohm environment in accordance with the manufacturer's instructions, and then you're done. However, it may be possible to optimize the performance of a design using a mimic LNA by applying the same concepts used for a discrete transistor LNA design. This approach can actually allow for lower noise figure than what the device manufacturer specifies. Here, we'll demonstrate the design of an LNA that uses the PMA 5451 Plus wideband mimic LNA from mini circuits. By using Modelithics models for this device and or passive components, we can optimize the design so that we achieve a lower noise figure than what the device datasheet specifies. We'll create this design using Keysight Technologies ADS software. Let's begin. As mentioned, we'll design this LNA with the PMA 5451 Plus mimic LNA from mini circuits. This device is rated from 50 MHz to 6 GHz. For this example, we want to design an LNA that operates from 3.3 to 3.8 GHz, which is the N78 5G NR band. Modelithics provides a data-based behavioral model for the PMA 5451 Plus device. Specifically, this model is an S-parameter model with noise. Shown here is the model datasheet. As you can see, the model predicts S parameters from 45 MHz to 20 GHz, and also noise parameters from 500 MHz to 8 GHz. Note that this is actually beyond the operating frequency range specified by mini circuits. Scroll through the model datasheet and you'll find S parameter plots along with noise model data. We can replicate these plots in ADS by simulating this schematic here. Shown here is the model itself along with 50 ohm input and output ports. Note that the model lets you select one of 3 different substrates. For this example, we'll select 20 mil Rogers 4350B. Let's simulate this, and now we can see the simulated 50 ohm noise figure and minimum noise figure. Let's look closely at our targeted frequency range of 3.3 to 3.8 GHz. We can see that the 50 ohm noise figure is 1.14 dB at 3.3 GHz and 1.32 dB at 3.8 GHz. At 3.3 GHz, the minimum noise figure is 0.82 dB, and at 3.8 GHz, the minimum noise figure is 0.89 dB. Therefore, our goal is to incorporate a suitable matching network so that the overall LNA design achieves a noise figure that's closer to the minimum values. A realistic goal, in this case, is somewhere between 0.9 and 1 dB. Now let's go back to the mini circuits datasheet for the PMA 5451 Plus device. We can see that the device datasheet specifies a typical noise figure of 1.3 dB at 3 GHz and 1.5 dB at 4 GHz. So we can see that our optimized design would achieve a lower noise figure than what the device datasheet specifies. So let's go back to our simulation and let's look at the optimum source reflection coefficient for minimum noise figure. The markers here indicate 3.3 and 3.8 GHz. Therefore, the matching network placed at the input of the PMA 5451 Plus must produce a source reflection coefficient that closely matches what we see here from 3.3 to 3.8 GHz. Let's also look at the simulated S parameters. You can see that from 3.3 to 3.8 GHz, S21 varies from about 9.8 to 8.7 dB. Now it's time to design the complete LNA circuit. Mini Circuits shows a recommended application circuit on the device datasheet. We'll base this design on that recommended circuit. You can see the ADS schematic here. Included, of course, is the PMA 5451 Plus model we've been looking at. And as mentioned earlier, this LNA is being designed using a 20mm Rogers 4350B substrate. Also included are Modelithics microwave global models for the capacitors, inductors, and resistor. Specifically, we're using AVX SQCS capacitors for C1 and C2, and Worth Electronic WEKI inductors for L1 and L2. Note that all the passive components in this design are 0603 sized parts. Since a single microwave global model covers the full range of part values for a vendor component series, these models are well suited for tuning and optimization. Let's focus on C1 and L2. These components represent the input matching network. Therefore, to achieve optimal noise figure, we'll need to properly set the values of these two components. Also, the lengths of the microstrip interconnects connecting C1 and L2 to the PMA 5451 Plus device play a role in achieving the best performance. So, in addition to properly setting the values of C1 and L2, we'll also need to tune the lengths of the microstrip interconnects. Let's perform an initial simulation by setting C1 to 100 picofarads and L2 to 390 nanohenries. We've also set the lengths of the microstrip interconnects to arbitrary values, as you see here. We can now simulate this and take a look at our results. We can see the simulated gain here. Notice how at 3.8 GHz, the gain is just under 8 dB. We can also see the simulated noise figure. Notice that the noise figure is slightly greater than 1.6 dB at 3.8 GHz. So, the next step is to optimize the design. Remember, our goal is to achieve a noise figure between 0.9 and 1 dB from 3.3 to 3.8 GHz. Now, it's important to point out that microwave global models include a discrete optimization feature in ADS. This allows designers to perform a discrete optimization in which the model's part value is adjusted to the optimal real-life manufacturer part value. We can use this design feature for C1 and L2 to achieve the best noise figure. So let's configure the optimization. We'll set an optimization goal of 0.9 dB maximum noise figure from 3.3 to 3.8 GHz. Now, it's generally recommended to perform a continuous optimization before performing a discrete optimization. Performing a continuous optimization brings you closer to the final part values, allowing you to focus on a more narrow range of part values for the discrete optimization. So let's enable C1 and L2 for continuous optimization. After we run the continuous optimization, we end up with these values for C1 and L2. Now we'll perform a discrete optimization by activating the discrete optimization feature for C1 and L2. Notice the range of part values we've chosen based on the results of the continuous optimization. Performing a discrete optimization results in these values for C1 and L2. This optimization process, combined with some tuning of the microstrip interconnects, lets us achieve optimal noise figure. We'll also want to adjust the values of C2 and L1 to achieve an adequate output return loss. So now that all of that has been done, we have values of 2 picofarads for C1 and 27 nanohenries for L2. C2 is equal to 3.6 picofarads, and L1 is equal to 3.3 nanohenries. Let's now look at the simulated noise figure. Now the noise figure is less than 1 dB from 3.3 to 3.8 GHz. For comparison, the dashed black trace shows the noise figure before optimization. Shown here are the simulated S parameters. You can see that the gain is about 10 dB at 3.8 GHz. So now the final step is to build the LNA and compare the measured data with the simulated results. This is a photo of one of the LNAs that was built. Let's first compare the measured S parameters of two different units with the simulated S parameters. The dashed traces represent measured data, while the solid traces correspond to the simulated results. We can see good agreement between the measured data and the simulated results. We can now see how the measured noise figure of these two LNAs compares with the simulated noise figure. Again, the dashed traces represent measured data, while the solid trace represents the simulated results. And again, we see good agreement between measured data and simulated results. So in conclusion, we've demonstrated how a design with a mimic LNA can be optimized to achieve a lower noise figure than specified in the manufacturer's datasheet over a narrower frequency range. This is made possible by Modelithics amplifier models and microwave global models for RLC components. If you're interested in using Modelithics models, please contact us for more information. Thank you.